Next, we want to prove Stokes' theorem. So this is a generalization of the fundamental theorem of calculus. Which is the following. So for simplicity, assume that f from a minus epsilon to b plus epsilon to r is a smooth function. So we just need once differentiable. Then integral a to b f dash d dt is equal to f of b minus f of a. So here we treat the space a comma b as a manifold with boundary the set containing of 2 points a and b. So we may view the above as integral over the boundary of m f is equal to integral over m d of f. So to make sense of in the integral over boundary of m of f, we have to give an appropriate orientation to the boundary. And let us see another example. Which is probably more relevant. Consider the upper half plane. So consisting of those points in R2 such that the y coordinate is greater than or equal to 0. Let U contain in R2 be an open set which contains H2. This is just for simplicity. Let F comma G from U to R2 be smooth, compactly supported functions. So consider the one form. F dx plus g dy on U. Let us fix the orientation . dx wedge dy on u. Then we have integral on h d of f dx plus g dy is equal to integral over h minus df by dy dx wedge dy plus dg by dx wedge dy. This, by the definition of the integration, is integral 0 to infinity, integral minus infinity to infinity, minus df by dy dx dy plus dg by dx dy. This is equal to minus infinity to infinity, 0 to infinity, dy dx, plus this term becomes 0 because g is compactly supported. And this term is minus infinity to infinity f of x comma 0 dx, which is just equal to the integral over boundary of h f dx plus g dy restricted to the boundary of h. So here we have given r equal to boundary of h, the orientation dx. So more gently, Stokes' theorem states that if M is an orientable manifold, with boundary delta M, and if omega is compactly supported, n minus 1 form, then integral over m d omega is equal to integral over boundary of m, omega restricted to boundary of m. So n is the dimension of m over here. So let us prove this. So first, let us set up some notation. Let Hn be the n-dimensional upper half space let U and V be open subsets of Hn. Let phi from U to V be a homomorphism. Let P be a point in the bound in U, which is in the boundary of Hn. Then we won't prove this fact. The image of phi of P also belongs to the boundary. So since otherwise, we will have that U minus P is homeomorphic to V minus phi of P, but U minus P has the homotopy type of a point, while V minus P, V minus phi of P has the homotopy type of a sphere. So throughout we will assume that n is greater than or equal to 2. We say phi is a smooth map if the following two conditions are satisfied. One, phi when we remove the boundary to Rn is smooth in the usual sense. And the second condition is for every point P in the boundary, there is a neighborhood U sub P of P in Rn such that phi extends to a smooth map from U sub P to Rn. So if both these conditions are satisfied, then we say that phi is a smooth map. We say phi is a diffeomorphism if both phi and phi inverse are smooth maps. A smooth manifold with boundary is constructed out of the following data. A collection of sets Ui where each ui is contained in Rn, and either ui is open in Rn or is an open subset of Hn. For each pair, I comma j, an open subset uij contained inside ui such that uii is equal to ui. For each pair I comma j, smooth diffeomorphism phi ij from uij to uji such that phi ii is equal to identity. And lastly, the cocycle condition should hold. Phi jk compose phi ij is equal to phi ik on uij intersection uik. The sets ui are glued using the phi ij. For each I, define the boundary of ui to be ui intersected with boundary of Hn, and define boundary of M to be equal to union of the boundary of the ui's. Clearly, boundary of M inherits a manifold structure. Since phi ij, when we restrict it to delta uij to delta uji, is a diffeomorphism. The open set M minus boundary of M is a manifold in the usual sense. If M minus the boundary of M is an oriented manifold, is an orientable manifold, then we claim that boundary of M is also orientable. So we see this as follows. First, choose coordinate open sets. U x1 through xn satisfying the following conditions, the following two conditions. First, dx1 up to dxn is the fixed orientation. On M minus the boundary, and 2, xn is greater than or equal to 0 on ui, and xn equal to 0 gives the boundary. Then delta ui x1 through xn minus 1 is a coordinate open set on delta m. We claim that dx1 h up to dxn minus 1 gives an orientation on boundary of M. To see this, we need to check the following. Star. Suppose u x1 through xn and v y1 through yn are two oriented coordinate open sets chosen as above. If P is in boundary of U intersected boundary of V, then dx1 wedge to dxn minus 1 at P and dy1 wedge to dy minus 1 at P are positive multiples of each other. So this is the condition star which we need to check, and that will show that the boundary of M is orientable. So let's check this. Note that yn is equal to 0 on boundary of U. On boundary of U, intersected boundary of V. Thus, delta yn, the partial derivative with respect to xi at P is equal to 0 for all P in boundary of U intersection boundary of V and I equal to 1, 2 up to n minus 1. So let P be in the intersection of the boundaries. Then dy1 wedge up to dyn at P is j phi at P times dx1 wedge to dxn at P, where phi from U intersection V to U intersection V, which sends x1 through xn to y1 through yn, is the coordinate change map. And j phi at P is the determinant of the matrix dy1 by dx1 at P, dyn by dxn at P, dy1 by dx2 at P. Sorry. So we have already seen that all these terms are 0. So what this shows is that this implies j phi at P is equal to j of phi restricted to the boundary at P times dyn by dxn at P. So since yn is greater than or equal to 0 on U intersection V, this forces that dyn by dxn at P is positive. Well, it is greater than or equal to 0, but we know that the Jacobian doesn't vanish, so it is positive. Or else we will have some point in U intersection V, some point Q, for which yn of Q is strictly less than 0. So thus, this shows that j phi restricted to the boundary of M at P is positive. Since dy1 wedge dyn minus 1 at P is equal to j phi restricted to the boundary of M at P times dx1 wedge dxn minus 1 at P, this implies that star holds. Thus, boundary of M is orientable. So, given an orientation on M, we choose, okay, so for n greater than or equal to 2, we choose, so let me write like this, given an orientation on M, dx1 wedge dxn, such that the boundary is given by xn equal to 0, the orientation we choose on boundary of M is minus 1 to the n dx1 wedge to dxn minus 1. So the sign is chosen to make Stokes theorem sign free. Sign free. So we have defined what is a manifold with boundary, and if our manifold, if M minus the boundary is orientable, we have described how to give an orientation to the boundary. And there's one more thing we need. What is a smooth? Is a smooth form on a manifold with boundary. As before, omega is said to be smooth. If omega restricted to the open set, M minus boundary is smooth in the usual sense. And if for each point P in the boundary, we say, okay, so not if, each point P in the boundary, we have a neighborhood U sub P of P in Rn such that omega extends to a smooth form on U sub P. So the picture is as follows. So locally it looks like this. So here's the boundary, this is the point P, and this is M. So what we need is, we need a small neighborhood U sub P such that omega extends to a form, smooth form on U sub P. So now we are ready to state Stokes theorem. Let omega be a smooth and compactly supported. N minus 1 form on M, which is a manifold with boundary. Then integral over M d omega is equal to integral over boundary of M, omega restricted to the boundary of M. Here delta M has the orientation described earlier. So throughout we assume the dimension of M is greater than or equal to. So let's see a proof. Let M equal to union Ui be a cover by coordinate open sets. and let Fi be a partition of unity subordinate to this. So by linearity of both sides, it suffices to show, to prove the result for Fi times omega. Thus, we may assume support of omega is contained in ui for some I. So there are two cases. First case is the boundary of ui is empty. Then we need to show that integral over m d omega, which since omega is supported inside ui, is integral over ui d omega. And since ui is an open subset of Rn, by the definition, this integral on Rn d omega is 0, because the integral over boundary of ui, omega restricted to boundary of ui, is 0. So this is what we will show on Rn. Omega can be written as a sum cardinality of I is equal to n minus 1 f sub I dxi, where Fi is compactly supported and we have already seen, we've seen this before, that integral d omega over Rn is 0. Well, so integral d j fi dxi is 0. So this this completes case 1. So next let's look at case 2. Here the boundary is non-empty. So in this case we have then integral over m of d omega is equal to integral over ui of d omega. And since ui is now contained in the upper half plane, this integral over hn d omega. So again, omega is equal to sum minus 1 f sub I dxi, and by linearity it suffices to consider the case omega is equal to fi dxi. So we further divide this into two cases. A, I is equal to 1 to up to n minus I naught, and I naught is not equal to n. Then it is clear that omega restricted to boundary of hn is equal to fi dxi restricted to boundary of Hn is equal to 0, since dxn restricted to boundary of Hn is 0, as xn is equal to 0 on boundary of Hn. So this implies that integral Hn is 0, so it suffices to show that integral over Hn d omega is 0. But d omega is equal to plus or minus df by dx I naught dx1 wedge up to dxn. And so integral Hn d omega is equal to plus or minus integral r n minus 2 integral 0 to infinity, and we can first integrate out the I naught variable, that's minus infinity to infinity df by dx I naught dx I naught, and then the remaining variables dx1 through dxn. But this is equal to 0 since f is compactly supported. And I naught is not equal to n. So next let's consider case B, where I is equal to 1, 2 up to n minus 1. Then so the conclusion is, in this case that is case A, integral over m d omega is equal to integral over boundary of m, omega restricted to boundary of m. So now let's consider case B. Here I is equal to 1, 2 up to n minus 1. Then d omega is equal to df by dxn dxn wedge dx1 wedge dxn minus 1. This is equal to minus 1 to the n minus 1 df by dxn dx1 wedge dxn. So integration over m d omega is equal to minus 1 to the n minus 1 to integral hn df by dxn dx1 wedge dxn. This is equal to minus 1 by the definition of, since we have fixed the orientation dx1 up to dxn, df by dxn dx1 to dxn this is equal to minus 1 to the n minus 1 integral of Rn minus 1 integral 0 to infinity. We will first integrate out the xn variable to dxn minus 1, which is equal to minus 1 to the n minus 1 integral over rn minus 1 minus f of x1 xn minus 1 0 dx1 to dxn minus 1, which is equal to integral over rn minus 1 f of x1 to xn minus 1 0 minus 1 to the n minus 1 dx1 to dxn minus 1. But then this is the orientation which we had chosen on the boundary of Hn. Sorry, this is not n minus 1, this is n. So this implies, so this completes the proof of the theorem. So let us end here.